This is our water tower design presentation. Hello, my name is Michael Guerra.
I'm Haydn Smith.
I'm Ryder Courtney.
Colton Burns.
And we chose Tombstone, Arizona because there is a relatively small amount of rainfall with an average wind speed of 8 miles per an hour, with a temperature reaching an average high of 94 degrees Fahrenheit and an average low of 36 degrees Fahrenheit. The population from the 2020 census was 1,308 people.
The issues with Tombstone's water supply stem from several things. Among these are its isolated location, arid climate, yearly rainfall of 13 inches, and the high tourism. Tombstone's isolated location with limited rainfall leaves it lacking a reliable source of clean water. Tombstone's current water source is starting to run dry. Tombstone has used a river as a water source for many years, but in recent years it has slowed and been drying up. And although the population is small, Tombstone is widely known for its tourism, and with this tourism, the lack of water is ever more noticeable. The residential population alone needs roughly 660 gallons of drinking water per day.
This is why we are trying to tap into the underground aquifer and pool water to fill our tower. Additionally, we would like to collect a portion of the rainfall and attempt to recirculate that back to the community. As Christians, we are called to care for those who are hungry and thirsty, and we have an obligation to ensure people's human needs are met. As Matthew chapter 25, verses 35 and 40 demand, for I was hungry and you gave me something to eat. I was thirsty and you gave me something to drink. Whatever you did for one of the least of these brothers and sisters of mine, you did for me. We are driven to care for our vulnerable communities and love our brothers and sisters. Everyone deserves the opportunity to better themselves, but that chance becomes significantly harder when their basic needs are not met.
For our shipping and design and assembly constraints, due to its extreme conditions for temperature, as well as Tombstone sitting about 70 miles south of Tucson and accessible by only three main roads, it limits the delivery options for large components, requiring us to optimize for modularity and efficient on site assembly, as well as materials that can withstand these temperatures. For our Design A overview, we chose galvanized 1040 steel to balance durability and capacity. The tank holds 771.7 cubic meters, or roughly 18,900 gallons, enough to supply water for about 28 to 29 days based on local demand. The dimensions are carefully chosen for stability: 5.56 meters tall, 3.5 meters wide. The trusses themselves have two cross beams from top right to bottom left, top left to bottom right, set to with the vertical beam set to about 11.36 degrees offset. The galvanized steel resists corrosion in Tombstone's harsh climate, while the compact footprint simplifies the transport and assembly under constraints we just discussed. For our simulations, the crossbeams showed to be zero force members and showed zero deformation under true scale conditions in SolidWorks. And our baseline performance shows even stress distribution, confirming the design handles the tank's static load efficiently. And under the average and double the average wind, these results did not change.
The hand calculations for Tower A, as you can see here, were made from one face of the truss and were done on this graph paper. Thus, we halved the wind load and quartered the tank force applied downwards. And for Tower A specifically, we had a roller to the left and we had a pin to the right. And all of these calculations were done in variable format so that they could be transferred easily into Excel to complete the rest of the calculations, as you can see here.
The design of structure B is very similar to that of structure A. We made sure to keep the materials, the dimensions, and the force loads exactly the same. The only real difference between the two is that in structure B, we took out the cross beams and replaced them with a single diagonal beam. That beam runs from the bottom left corner of the base to the top right corner. This setup lets us see how that one design change affects the overall strength and stability of the structure while making it more affordable to produce because there is less overall steel being used. When looking into the simulations, uh, we used a true scale simulation and ran it under very specific conditions. We tested three main wind scenarios, no wind, average wind, and double the average wind. And for each of those, we also ran their own sub simulations to see how the water tank would perform with only half capacity and then with full capacity. This gave us a more complete picture of how the structure holds up under the different levels of stress and environmental pressure.
Similarly to Tower A, Tower B was designed to be conservative on materials and overall size, leaving a relatively simple design and free body diagram that you see before you. The image shows a single face of the four-face design with a pin at point A and a roller at point B. The wind force is placed on the main crossbeam on the top, and the two forces representing the tank are pushing down on either corner of the top of the tower. The total height of the truss alone is 2.5 meters tall and roughly 3.5 meters wide.
After completing both hand calculations and simulations for designs A and B, we calculated the percent error between those two calculations using our SolidWorks data as the theoretical reference. As you can see from point A, design A, the majority of percent errors were pretty low, with the lowest being 1.1 and average being 34.41. However, as you can see from FAD and FBC, those values are 100% error. That is because in the hand calculations, we got 0. However, my SolidWorks simulation gave a very small number, and because of how percent error is calculated, it gave us a 100% error. So if we removed those from the equation, the average percent error for A would only be 1.6. For B, however, it seems to be larger, with the lowest being 43.04 and the average being 49.6. This high percent error could have possibly been caused by incorrect SolidWorks simulations or hand calculations. We were unable to diagnose the problem as multiple people tried to figure out why the percent error was so high.
For our design selection process, Tower A's galvanized steel construction does carry a premium, about $1,400 more than Tower B, but this investment buys a critical advantage. Tower A's average percent error in simulations was 34%, significantly lower than Tower B's 49%. This means more predictable behavior under stress. The added crossbeam in Design A creates a stiffer base, crucial for handling Tombstone's temperature swings and wind loads over the decades. In infrastructure, reliability outweighs short-term savings. Tower A's durability and lower margin for error make it a clear choice for Tombstone's water security.
This is the bill of materials that is meant to cover everything we would realistically need to complete this project from start to finish. Again, we decided to go with design A because the percent error between the hand calculations and the simulations was much smaller, meaning the result was more consistent and reliable. The overall cost for this design is slightly higher, but we believe the improved accuracy is worth the trade-off. We have made sure that all the essential building materials, such as steel, concrete, pipes, and bolts, uh, were factored in, and we also considered that the equipment needed by the crew, such as welding tools, excavators, and cranes, were also included on the budget sheet. Once the tower is built, we want it to last and truly serve the community and not fall apart over rust and time. That is why we are using sealant and primer paint to prevent corrosion and we also want to make sure that every worker gets the proper personal protective gear to keep the job site as safe as possible.
To start the assembly, we must get approval from the state to build the water tower and approval from the water department. After this, we will gather funds and hire a team that knows how to build the structure. We will buy the materials needed and rent the tools we'll need to assemble this, bringing everything to site and organizing it so we'll be ready to move as quickly as possible. We'll build the tower frame by connecting and welding the beams together and attaching the water pipe that'll carry the water from the tower to the town. Seal all the pipes with silicone at the metal connectors and paint the outside of the tower with primer paint to stop it from rusting and corrosion. After any final safety up parts like ladders and access panels are added, a schedule will be set up to maintain the tower.
Thank you.
Thank you.
Thank you.